Hello. So in this video, we're going to look at Haberman's section 3.2, and I guess technically pieces of section 3.1. But in general, the goal for the next few kind of sections is to talk more about these Fourier series that showed up kind of in the last section when we were solving the heat equation, as well as you can use the same techniques to solve the wave equation. Okay, but these Fourier series, they showed up when we were trying to match kind of the heat equation, I guess, as well as Laplace's equation, when we were trying to match them to initial conditions, right? So plug in t equals 0, kind of those exponentials go away, and you were just left with, a sum of a constant times a trig function, right? Multiply both sides by the trig function, integrate, isolate the constant. Great. So, right, we worked with Fourier series already. And now the question is, how far can we take these objects? What else are they good for? What more can they tell us? Etc. Okay. Right. So in the last section, we made you might say a bold assumption, right? Where for a function f of x on some interval, right? And usually when the interval had these bounds, we were looking at kind of a circular ring or something, but right, change the bounds, doesn't really matter. But in section 2, right, we were looking at a function on an interval, and we assumed that the function f could be written in this form, right? Where you have some constant, a bunch of these cosine terms, and a bunch of these sine terms. Okay, in some sense, this constant also fits in with these cosine terms, but whatever. So we assume that a function could be written in that way, and then it was just a matter of computing what these coefficients were. And we have formulas for those things. So the first coefficient is this thing, second coefficient is this, third coefficient is this, right? So nothing new yet. Okay, but we were working with these things as if there was an equality. Okay, so the main question we're asking now is, well, when does this equality hold, or does this equality hold? Okay, another aspect of this question is, let's see how much space I have. So maybe another aspect of this question is, if instead of kind of up here, if instead of computing these infinite sums, if instead you just said, well, I want to compute it up to maybe the first, maybe big N terms. Okay, so make some approximation, and then let capital N go to infinity. Do you get convergence of this trig series to the function? Okay. So those were questions we ignored, okay? But they're important questions, right? We're using this technique. Is it actually a valid technique? And so kind of before we kind of address this question, right? When does this equality hold? One thing to kind of point out and maybe notice is, right, well, even if our function f is defined for this interval negative L to L, right, which is kind of that interval that we really care about. When we compute this Fourier series, right, we get these sine and cosine terms. These functions, we can plug in whatever we want, right? We can plug in x between negative L and L, or we could plug in much larger values of x, or right, values of x going off into the negative direction. Okay. Right, so these trig functions that we use to build up our solution, a priori, they're defined for all possible x. But if we kind of go outside of these bounds, negative L and L, right, then sine and cosine don't behave any differently, right? Sine and cosine are periodic, okay? And we just pick that domain that we care about that matches up with the domain of f. But in a sense, this Fourier series that we define, right, is defined everywhere, and it's periodic, right, on the entire real line. So in some sense, you might say that this Fourier series gives a sort of extension of this function f to the entire real line. Okay? Sometimes we care about the fact that it's an extension to the whole real line. Sometimes we don't. Sometimes we really just care about the interval negative L to L. But just something to keep in mind, right? Working with these functions, we kind of extend the domain of X that we're allowed to plug in. Okay. So back to the question. So, right, what was the question? When does this equality hold? What was this equality? A given function on an interval is equal to this series. Okay. When does that hold? Okay. So we won't actually prove it, but we will state kind of what's needed. And the nice thing is that in practice, any function, any whatever that you'll be working with will satisfy this assumption. Okay. So for every function that you'll see in practice, this can be done. It's equal to the Fourier series. Okay, so what is that condition? Well, we need f to be piecewise smooth. Okay, which, you know, in your head, you can think of just continuous and smooth right now, not necessarily worry about this piecewise part. Right, but what is this piecewise smooth? Well, it's the same thing as being kind of piecewise continuous or piecewise linear or whatever. It's just now on those pieces, we require the function to be differentiable. Okay. And another thing to note is that just because we're saying it's piecewise smooth, the function f doesn't necessarily need to be continuous. Sometimes when people say piecewise smooth, they mean continuous and piecewise whatever. Here we just mean on the pieces it's smooth, but those pieces, there may be jump discontinuities. Okay. Okay, so if f is piecewise smooth on the interval we care about, then f converges to one of two things. Either one, it converges to this periodic extension of f to the whole real line, wherever this extension is continuous. Actually, I should clarify. So this should say then the Fourier series. There we go. So here, think of this as plug in a big capital N for the series, take that finite sum, capital N go to infinity. If you look at that object, then the Fourier series will either converge to this periodic extension of the periodic extension of f, wherever this extension is continuous. What about the discontinuous pieces? Well, for the discontinuous pieces, the Fourier series is going to converge to the average of the left and right limits. Okay, not the left and right function values, but the left and right limits. And we'll draw some pictures of this here in a second. Okay, but what I want to do first is clarify this piecewise smooth and this periodic extension stuff. Okay, so as I kind of mentioned above, when is a function piecewise smooth? Well, it has to be differentiable everywhere except for finitely many points. And as I mentioned, doesn't necessarily need to be continuous. Okay. So an example of a piecewise smooth function might just be something like that, and then maybe there's a jump discontinuity, and then something like that. Okay. So everywhere except for this jump discontinuity, right, the function is both continuous and differentiable. And we don't really care what happens here. We just need kind of away from this bad point. It needs to be smooth. Okay. Okay, so that's that definition. The other thing that we had was this notion of a periodic extension. Okay, and I kind of got at this with the sine and cosine bit before, but a periodic extension of a function f defined on an interval negative L to L is going to be, well, essentially f, okay, just copied over a bunch of times. Okay, so one way to formalize that is we say, well, we define kind of this new function f so that if you're at a kind of a piece of the interval, maybe like n pieces over, okay, well, what is the value over here? Just look at the corresponding value in that fundamental block. Okay, so you could think of this as take the graph of f from negative L to L, copy it over to, say, L to, in this case, 3L, then copy that over from 3L to 5L, etc. Okay, and so here, maybe so a sketch or a picture of what you're just describing. I'll here. So if this is minus L, maybe this is 2L, this is 0. So let me make 2L. 2L, 3L, go back the other way. So 0 minus L minus 2L minus 3L. Okay. So maybe our function looks something like that. Yeah. So then the periodic extension of this function will be, so copy the same profile over there, copy the same profile over there, something like that. Okay. Right. So what I was saying up here is that, well, what does the function value say at x plus L? So maybe this is x, and then we add L. And so then we end up 1 plus L, give me 1 second. This should be, x plus n times 2L. There we go. We need the full period. Okay, so, right, if this is x, right, and this is that function value f of x, well, if n is equal to 1, say, for example, then over here, x plus 2L, that's going to be, so this is x plus L, x plus 2L. So we're going to have this point right here. What's the function value at x plus n 2L? Well, that's going to be the same function value, f of x, which is what we've indicated right there. Okay. So this periodic extension, just take the graph of f, translate it, by 2L in either direction, which is what these sine and cosine terms do automatically. Okay. Okay. So back to the statement of the theorem, right? So if f is piecewise smooth, okay, then the Fourier series either converges to the periodic extension, wherever that's continuous, or the average of the two values where the extension is discontinuous. Okay. So one way we can write that is the following. Okay. So this is for values of x within that kind of fundamental domain, negative L to L. This is going to be kind of a limit from the left or from below. Say x is below the, I don't know, limit point, and then we go towards the limit point from the left. X minus, you could say x is decreasing to the limit point, or x starts at the right, goes back. So in this interval, we have this equality, okay, where what are these things written out? So f of x plus is the limit of f from the left. F of x minus is the limit of f from the right as z decreases down to x. Okay. So one thing to note is that, well, right, wherever f is continuous, okay, then, right, the limit as z approaches either side is going to be the same, right? I mean, that's one definition of continuity, okay? So if f is continuous, then this term right here is going to equal this term. So what do we end up with? Well, this plus the same thing, so twice f of x divided by 2, which is just f of x. And the theorem tells us that that's equal to that. And then the difference is, well, wherever f is not continuous, these two values won't be the same. And then this gives the average of the two. So as an example, if we want to sketch kind of what's happening here, right? So purple, this is equal to the Fourier series a sub n, say cosine of n pi over Lx plus sum of b sub n sine of n pi over Lx. Okay. Right, so the theorem says that wherever f is continuous, so it looks like along here, f is continuous. Kind of what does a Fourier series give us when we plug in values of x? Well, it's going to give us the exact same value of f. Okay. Likewise, that's meant to be on top of one another. Likewise here. Okay. So wherever f is continuous, this Fourier series is going to be exactly equal to f. The difference is where f is discontinuous, which happens right here. And the theorem says that, well, what is the value of this Fourier series at this discontinuity? Well, it's going to be the average kind of right, the left limit and the right limit. So just take the values you'd expect these two places, take the average, that's the Fourier series in between. Okay. Right, so the observation is, right, well, the function f and its Fourier series don't always agree. Right, up here, right here, f takes this value, the Fourier series takes this value, okay? And so since they don't always agree, we're going to introduce some notation to kind of, right, keep these two objects separate. And so what we'll do is we'll write f of x tilde kind of the series to mean exactly that this object right here is the Fourier series for this function f, right? Where a0, an, and bn you can compute as before. Okay. So we kind of sketched the Fourier series. Okay. So what we're going to do now is just kind of formalize that process. So how do we sketch a Fourier series? Well, so there are 3 steps. 1, sketch f, kind of on the interval that we care about or that we're given. Sketch the periodic extension of f, which just means right? Take that profile of f, copy it over a bunch of times to the left and right. And so wherever that, right, kind of periodic extension is continuous, well, that's the Fourier series, or that's equal to the Fourier series. Wherever that extension is not continuous, right, the Fourier series takes on the average of the two values. So the third step is, well, you can mark an X, and the book likes that, or you can indicate however you want that the value of the Fourier series should be the average of the two values at that jump discontinuity. Okay. So let's look at some examples. Okay. So here we're given a piecewise continuous function, okay, and we're told L is equal to 1. So what is the interval we're working with? Do something like that. So x equals 0. This is going to be minus L to L, 2L, 3L, minus 2L, minus 3L. Okay. Okay. So we want to sketch the Fourier series. First bit, sketch f on the interval. What is f? Well, it's 1 between -1/2 and 1/2. So I can, here, let me clarify this. So L is equal to 1. So these should all be -3, -2, -1, 1, 2, 3. So if we want to sketch a Fourier series, so it's going to be 1 between about -1/2 and 1/2. I should draw the y-axis. So the y equals 0, y equals 1 is right about there, etc. And then it's 0 here, 0 here. Okay. So we sketched f on the interval. Okay. Next bit, sketch the periodic extension of f. Okay. Right, as I said, take the same profile, copy it over into these other kind of blocks of length 2L. I mean, another way we can kind of go about this is say, well, right, we want a periodic extension of f. So one question is, right, what would be, say, f of 2, for example? Okay. Well, the period for this function is exactly 2, right? I mean, that's our fundamental domain. That's kind of the piece we're saying, kind of, here's the profile of f. So, for example, if we wanted f of 2, right, this is going to be f of something in our fundamental domain, so something that has a value between -1 and 1, plus twice L, which is going to be, again, f plus something in our fundamental domain. In this case, L is 1, so this is going to be f plus 2. Okay. So if we subtract off twice the period from 2, right, what are we left with? 0. Okay. So the piece that goes in here is kind of 0, right? So what is the value of f at 2? Well, if we want a periodic extension, this should just be f of 0. And if we look back here, f of 0 is exactly 1, which we can also read from this. So the value of f around here is going to be about 1. Okay. You can do the same thing with other points. And so what you should end up with is about like halfway between those two things. It's going to be 1, else it's going to be 0. Okay. Do the same thing over here. It's going to be 1 about there, 0 kind of in there. Okay. So we've sketched the periodic extension. Last bit is we're going to mark kind of the value at the discontinuities. So there are two ways discontinuities can arise. Either they arise kind of in the interior, right, where the function already isn't piecewise smooth, or depending on the function, these discontinuities can arise at the ends of the interval, okay? And that's actually something that we saw in one of these other sketches here, right? That's a discontinuity, etc. Okay. So when we go to sketch the jump discontinuities, really we just need to look in the fundamental domain, right? Negative L to L. Just need to look in this region right here, figure out the discontinuities there, mark the X's, copy those to every other piece. So in this case, there's that, and these occur with value, say 1/2. So we've marked those, copy them over. At the ends of the interval, so over here, f is 0. Over here, the periodic extension of f is 0. So it's continuous over kind of the boundary of the domain. So no issue there. Okay. And we're done. This is the Fourier series of our function f. And one thing to maybe start thinking about is, well, so when we're working with Fourier series, right, really what we're doing is we're working with something like sine waves. Then maybe I can and so this is a sine wave of a higher period or a higher frequency, maybe in even higher frequency one that you can barely see because it's yellow. So we have sine waves. We also have cosine waves, which are going to look not nearly as nice, but something like that, etc. Okay, so one thing you can start thinking about is, well, right, what we sketched here is this infinite sum of cosine and sine terms. Okay, so what might that convergence actually look like? So this is something that you can play around kind of in Python or whatever other language, but right, if you add up infinitely many terms, this is exactly the thing that we're going to get. So another example, we can do sine of x. So one thing to keep in mind is, well, sine of x is already a periodic function from negative pi to pi. So we'd expect that its Fourier series should just be itself. But that's something that we can check. 2 pi, pi. I'll just go in that direction. Okay, so what is sine of x on this interval? Well, something like that. Okay. So here we sketched f on the interval, right? Now we're going to sketch the periodic extension of f. And for that, what we're going to do is take the same profile. Let's see if I can do it like this. And then copy, no, I'll redraw it. Take that profile and then just copy it over, right, to the next block. And then you could also do that going the other way. Last step, mark an X at any jump discontinuities. Well, looking back here, everything's continuous. We're good to go. That's the Fourier series for sine. Okay. So the last one, which is slightly more interesting, is, well, same function. Just now we're working on a different interval. Okay. So now I'm saying define sine on the interval negative pi over 2 to pi over 2. and take its periodic, and then sketch its Fourier series. Okay. So in this case, since we're not working from negative pi to pi, the Fourier series of sine of x is not going to be equal to sine of x. Okay. And again, it's because we're working on kind of a different sort of interval. Okay. But again, right, process is the same. So starting point, right, sketch f on the interval, and then sketch the periodic extension. Okay. So what is sine of x on this interval? Well, sine of x kind of goes like that. If we were sketching sine of x from 0 to pi, then we'd also draw that, right? But we're only defining sine on the interval negative pi over 2 to pi over 2. So that piece we don't have. Going the other way, it's going to look something like that. Okay. So this is our function in the interval negative pi over 2 to pi over 2. For its periodic extension, take the same profile, copy it to the left and right. So we're going to get something like that, and then something like that. Okay. So that's the periodic extension. Last bit, compute the averages of the jump discontinuities. Where are the jump discontinuities? Well, in this case, the jump discontinuities are exactly at the ends of the intervals. Right? This value is 1. This value is -1. The average is going to be 0. And then it continues on like that. 0. And it continues on like that. Okay. So this is the Fourier series for sine of x defined over this interval. So, right, one thing to note is that when we visualize Fourier series, we don't need the coefficients. Okay. Like here, we can compute the coefficients for this Fourier series, right? And again, they look like, I can scroll back up, right? These are the Fourier coefficients, so we could plug in, right, negative pi over 2 to pi over 2 of sine of x, compute all of these, and right, get that explicit series. But if we wanted to sketch what that series looked like, we didn't need those coefficients at all. Okay. So when we visualize these Fourier series, we don't need the coefficients, but it's still important that we know how to compute them. If we actually want to write out solutions and kind of do things analytically, it's a skill we need to utilize. Yeah.